All right, guys, we're gonna go ahead and get started with today's notes. Hope you had a good weekend. Today we are just gonna go ahead and start looking at just more series tests. We just have 2 more to learn this week. We'll finish those up tomorrow, and then Thursday is gonna be a review day, and then your your quiz is on Friday. Tests we have learned so far, so we have the nth term test, which is really a test for divergence. We have the geometric series test, the p-series test, and then we did our 2 comparison tests, the DCT, the direct one, and then the LCT, the limit comparison test. Today we are going to be looking at what's called the alternating series test. I will say this is the one series where we have to know a little bit more about it. So we are going to have some other definitions. There are actually different types of convergence that we can have. And then the alternating series is one where we don't have a formula to find the sum of it, but we will have an error bound where we'll be able to figure out that the actual sum is between a certain interval. So let's go ahead and talk about the alternating series and just define it. In simplest terms, when I say an alternating series, I think by its name you can assume that it is alternating something, and what's alternating is going to be the signs. So an alternating series is going to be a series whose terms alternate signs. These type of series are actually going to be pretty common to us in the second half of the unit when we start doing a lot of what we call Taylor series and Maclaurin series. But basically, if you see terms going back from plus, minus, plus, minus, plus, minus, then that is going to be a type of alternating series. They can show up different ways. So I try to think of 3 examples of how these alternating series kind of show up. And these are 3 ways we often know that we are dealing with an alternating series. This first one is technically also a geometric one. So some geometric series can also be alternating series. Like this one, you're basically multiplying by that negative 1/2 over and over and over again. It's like looking at the terms, plugging in 0, we have that, plugging in 1, plugging in 2, and then that's going to basically continue forever. That would be considered an alternating geometric one. That one you technically could prove whether it was convergent or divergent using the geometric series test, which is what I would definitely use. But we would be able to also use the alternating series for it, for both of them. The most common way we're going to see an alternating series, though, is this middle way, where we have basically the negative 1 raised either to the n or to the n plus 1. So if I'm looking at this series, plugging in 1 for n where we're starting at, that makes 1 plus 1, 2. So that numerator will be positive 1, switches to negative 1, positive 1, negative 1, and then the denominator is doing its own thing. And of course that would continue forever as well. There's also some other ways you can get alternating series, and the third common way, is probably the least common way, is going to be using trig. So this last one would be alternating because we're starting at n is equal to 0. So your denominators are doing one thing. So I'm starting with 0 plus 1, 1 plus 1, and so on. In the numerator, though, we're going up by 1. So we have the cosine of 0, which is 1, cosine of pi, which is negative 1, cosine of 2 pi, which is positive 1, cosine of 3 pi, which is negative 1, and then that would continue forever. Ian, you had a question. You're good.
How would you find determine convergence of that middle one?
You would use what we're doing today, the alternating series test.
Oh, right.
So yeah,
I forgot that one.
Yeah, we're learning that today. So this one I would definitely use the absolute value of r is equal to 1/2, which is less than 1, so it converges by the geometric series test. But technically for all 3, we could also use what's going to be called the alternating series test. And what is that alternating series test? I'm going to go ahead and just give it to you, so I'm going to skip ahead in my notes. The alternating series test does have kind of 3 requirements. And so how we prove them is going to look a little bit different. The three requirements, the first one is kind of duh. Your basically terms have to alternate signs, which if your terms don't alternate signs, then clearly you're not using the alternating series test. The other thing that has to be true is the limit as n goes to infinity of your terms has to be equal to 0. So those terms, they are switching back between plus or minus, but they do both have to be getting closer and closer to 0. And the third thing that has to be true, I don't know why my pen's not working today because it's dead, is terms decrease in absolute value. And I'll explain kind of what that third one means. And that often is like the third one that's like the trickiest to prove. So basically what can happen, so I have 4 cases of what can't happen. So first, if the terms don't alternate, then clearly don't use this test. If the limit of the terms is not 0, clearly don't use this test, but from a previous rule, what do we know if the limit of the terms is not 0? What do we know about that series automatically? It diverges. What test is making it diverge?
Nth term.
The nth term. So that's really just the nth term test. If terms don't decrease in absolute value, then the alternating series test gives no info. And then the last one, most important one, if option 1, option 2, and option 3 are all true, then the series is going to converge by the alternating series test. How do we prove these? We often just have to like state them. So like that first one, just say, hey, terms alternate signs. Like saying that sentence or that statement is good enough. Showing the limit is equal to 0 also is all you have to do. Like write the limit expression, show is equal to 0. Option 3, there's 2 ways to show option 3. And when I was grading AP exams, there's more than 2, but there's like 2 that I readily saw, and they're both equivalent. I'll switch back and forth between the 2 because they honestly do kind of mean the same thing. The option 1 that you have is you basically will have to state what the absolute value of the terms is. So basically you just drop off what's causing the signs to rotate back and forth between positive and negative. Write that statement and then say something like, this value decreases as n gets larger. That's one option. Again, there's no way to like prove it. You just have to state it. Again, if you want to like look at it and make sure that's true, but that's one thing you want to do. The other way, which is I think a little bit of a stronger way to do it, is to actually clearly show that it is decreasing in absolute value. And what I mean by that is you want to find the absolute value of a sub n. And then you also want to find the absolute value of a sub n plus 1. When you're thinking about it, a sub n is one term. What would a sub n plus 1 represent? The next term. And if it's decreasing, then you would just want to show the statement that a sub n in absolute value is bigger than the absolute value of a sub n plus 1. And you just need to write that statement. And of course, check to make sure it's true. But that's basically the 2 ways we can kind of show that third option. And then if all 3 are true, then just converges by the alternating series. Yes, Ian?
So if you had an alternating series where it was like, you know, the -1, 1, -1, 1.
That would,
Technically, you could use this, and then that would be the middle one, right? It would diverge.
yeah, it diverges by the nth term test. So let's go ahead and look at an example. And I did phrase this example a little bit differently. So the first question might say these questions often have two parts. And the first way is going to be like, hey, does the following series converge? And so that's going to be like what I have kind of typed in blue. And then in parentheses is also another way this question would be asked for the alternating series. Now, of course, define these terms in a second. Instead of being asked whether a series converges, you might be asked, does the series converge conditionally or absolutely? So we're going to see some more vocabulary when it comes to these alternating series. Because weird things happen when you have alternating series. Like you just think about the terms, you're going to have like maybe a positive term, then a negative term, positive, negative, and you're hoping that they get closer and closer to zero. But kind of that back and forth motion of the terms can just cause like weird things to happen mathematically. So let's go ahead and look at this example. I have a clean slide of it. And so let's go ahead and state whether the following series converges. So I'm looking at this one. We have the series. It's -1 raised to the n plus 1 over n. Well, which test do we want to use? Like, you can go through all the options, but if I see something like -1 raised to a power, I know automatically that these terms are going to alternate. Like, we could find them if we wanted to, but I can see that this is alternating. So let's go ahead and use the test. If I'm using the alternating series test, I just need to show options 1, 2, and 3 are altered. So first option, I'm just going to state series terms alternate signs. I don't need to prove that. I can just look at it, but I do need to make sure I say that statement. Option 2, what's the second thing I have to show is true? The limit does approach 0. So I have the limit as n goes to infinity of my terms. Well, looking at this one, that -1 is the one switching back and forth between +1 and -1. So what's going to matter most is that denominator. N is going to infinity, the denominator is going to infinity, so what are the terms going to overall? 0. So far we're so good. The terms alternate signs, the limit does approach 0. And then we do want to show that the terms are decreasing in absolute value. Two ways to do it. So option 1, I'm going to go do both of them, is you want to state clearly what the absolute value of a sub n is. So you want to look at that. If you take the absolute value, what technically is that numerator just going to be?
1 to the
1. And technically, I'm not going to worry about the n there when I do the absolute value, because what's 1 to the nth power? Always going to be 1. So that numerator in absolute value is technically just 1. The denominator is just n. So that's the absolute value of the terms. First way to do it is you just look at this. Imagine n is getting bigger. As n gets bigger, what is that expression doing? Is it getting bigger or smaller? It's decreasing. So we have our absolute value. We're going to say that this decreases as n gets larger. That's one way to say it. Some students prefer the verbal way. Personally, me just being more of like a math person, the other way to do this one is you want to state the absolute value of the terms. You want to state the absolute value of the term that comes immediately after it. And then want to state clearly which one's the bigger one. Well, which one is going to be the bigger one? The one on the left. So you think it has the smaller denominator, so it is the bigger one. So what is that basically saying? Every time you have one term, the term that immediately comes after it is going to be small. Either of those statements work. I don't care which one you use. All three of those statements are true, so I can say, so series converges by the alternating series test. Some students like the alternating series test, but there's not really a lot of calculating you have to do. Like, it's not one of the comparison tests, it's not like the limit comparison test. You just have to just know the statements to say and kind of go through. And again, with those threes, you want to do one or the other. They're both kind of equivalent statements that work. Questions on the alternating series test? So that's all. Yes, go ahead.
What would you have it that like 2 and 3 are like one's met than others?
To be completely honest, for that third one, if you're using the alternating series, I haven't seen one where the terms don't decrease. And the issue with this is like we often don't deal with like the super complicated series. So like it does make sense, like you're kind of looking at two and you're like, well, if the limit is approaching 0, it would make sense that they would have to be getting smaller and smaller each time. Ones where that wouldn't be true are often going to be ones where the term that's causing it to go from positive to negative is a lot more complicated than that. So like if there had been like an actual function kind of plugged into that raised to n+1, and that's what's caused it to kind of go bounce back and forth, that's what's going to cause 3 to fail. And to be completely honest, I have not seen one where, when we did the alternating series for calculus, where 2 is true and 3 wasn't true. But technically there are functions where that wouldn't be true, so you do just want to make sure you kind of just write all 3 down. But that is a good thought process. Like most of the time, if 2 is true, then 3 is also going to be true. Yes?
Do we know what the series converges to?
So we'll get to it at the end of class. For an alternating series, we can't know what it exactly converges to. I mean, like what is the actual sum, but we can come within, like you can pick how accurate you want to be, and there's a way to figure out how many terms you need to add to be that accurate.
Okay.
So when it comes to the alternating series, since it is a weird series, there are going to be 2 different types of convergences for it. So like when we talk about a series, that series can either converge, or we know that that series can diverge. And that's basically what we've looked at so far, is that we have convergent series, and then we have divergent series. Convergent series does have 2 different types of convergence. We have what's called the absolute convergence, and then we also have something that is called conditional convergence. And the best way that I can describe the difference between it is an absolute convergence is going to be a stronger type of convergence, and we'll define it in a second. And conditional convergence is going to be like a weaker, if not like a weirder type of convergence as well. So it's not going to be as strong. It still converges, just not as directly as one that converges absolutely. Often on the AP exam, you're going to have to figure out if a function is, if a series is absolutely convergent or conditionally convergent. So let's go ahead and formally define those. And a series that is absolutely convergent, we're going to say some series converges absolutely if and only if the series with the absolute value of the terms also converges. So a series is going to converge absolutely if the series involving the absolute value of the terms also converges. From this, you can kind of conclude if all terms are already positive, then it is absolutely convergent. And I probably should be more clear, already positive and converging, but. Which should make sense. If all your terms are already positive, then the absolute value of the term is literally the same series. So it's going to be convergent absolutely. So most of the series we've done that we have talked about have already been absolutely convergent. A weaker type of convergence is going to be conditionally convergent. And something that is conditionally convergent, we're going to say the series is conditionally convergent if and only if the series itself converges, but the series in absolute value diverges. And again, why we're calling that conditionally is this is going to be like a weaker, kind of looser type of convergence. There's a lot more kind of a technical thing going on right now, but for us in this class, just thinking of it as like a weaker convergence is going to be okay. And basically the difference that we have, if something is going to be conditionally divergent, I'm just going to leave that short answer. Like it's going to be just like a weaker type of convergence. We often just need to be able to classify it. So how does this look like? We're going to use that same problem that we just did. So we already showed that this function is convergent. Like that's the same series, the same function. We've already shown that that series is convergent. If we want to be able to classify it as absolute or conditional, we just need to consider the absolute value of the terms. So again, we already proved that this is convergent. We said this was convergent by the alternating series test. But if I want to prove whether it is conditionally convergent or absolutely convergent, I do need to consider basically the absolute value of the series. So we're going to consider the series. And again, this will be the absolute value of the series, which again, what's causing it to be in positive or negative, mainly that thing in the numerator. So looking at the absolute value of the series, that is 1 over n. What series is that 1 over n? It's the harmonic. What do we know about the harmonic series? It diverges. You don't have to use a proof. So this series is 1 over n. That series is harmonic, so diverges. So the original series, is it going to be absolutely convergent or conditionally convergent? Conditionally. And there's two ways to say it. You can say so the original series is conditionally convergent, or the original series converges conditionally. What is that condition? It only works when it is alternating. Once you take away that alternating aspect, it stops being convergent. Which again, I think is kind of a weird thing. Like when the series is kind of acting crazier, going up and down, up and down, up and down, it converges. But once you take away that absolute value and just look at the positive terms, it no longer is convergent. So it's kind of like that plus or minus balanced out what needed to happen for it to work. Questions on absolute convergence? Yes?
Do we need to say like why it's conditionally convergent? Is there anything like by all velocity?
No, that works. As long as you've shown that the absolute value diverges and it's conditionally, if your absolute value is convergent, then you just say then it converges absolutely. So then the other thing we want to look at with the alternating series test, excuse me, let me go back to the name series. So we use the alternating, no, let me start over. We just use the harmonic series, and again, that is a memorized series. I did want to give you a slide. We have 3 series that exist that you never have to justify your answer for. So you can always just call it by its name and say what it is. This first one, kind of we already talked about it. What's the name of that series? Harmonic. Again, you never have to justify this one. You can simply state that it is harmonic. What do we know about all harmonic series? It is going to diverge. You never have to justify your answer for that. The one that we just did is also a named one that from now on we never actually have to justify our answer for. What do you think the name of that series is going to be? Which one did it look like? It looked like 1 over n, but it's alternating. So what name does it have? Alternating harmonic. Not exciting. So this is the alternating harmonic series. Again, we could justify it, but this is one that the AP exam considers to be a memorized series. What do we say this series is? It is convergent. Technically, it converges conditionally, but knowing that it converges is important to know. Why is that useful? Maybe you want to use it for like a comparison test, but again, you don't have to ever justify an alternating harmonic. And then the last one that you never have to justify, even though you just prove it with the nth term test, is this term where it is alternating, but it's just switching between 1 and -1. This one has a name, it's named after a mathematician, it's Grandi or Grandi series. It diverges, and technically you can use the nth term test to prove that. So again, not really one that's probably worth memorizing because it's easy to prove, but it is one that it does exist, and we know that it's going to diverge. So again, any of those three, you never have to justify your answer. You can just state what it is, and then state whether it converges or diverges. Last thing we have with the alternating series is something called the alternating series error bound. College Board loves this type of question, and I'm going to show you two different ways that they often ask it. And this goes back to, Sam, your question you asked earlier. So for us, the only series that we have a formula to find what it actually adds up to is the geometric series. It's the initial term over 1 minus r. For an alternating series, and this theorem only works for an alternating series, we do have an error bound where if we want to find the sum, we can basically figure out like how exact we need to be. Do we need to be exact like 0.1, 0.01, 0.001, and use that error bound to figure out how many terms we need to add up to be exact to some certain value. So what that theorem states, it says, suppose the series of a sub n is an alternating series, and it converges to a sum of s. That's going to be the exact sum of it. And we don't really have a way to find the exact sum, but we're just saying, hey, that is the exact sum. If we approximate using a partial sum, so I have s of k, so instead of an infinity sign at the top, we're just stopping at a certain value, then this following statement is going to be true. And I'm going to write it two different ways. I'm going to write it both verbally and then kind of in the notation. And the formula is s minus s sub k, and that's an absolute value, is less than or equal to a sub k plus 1, and it's the absolute value of a sub k plus 1. What does that mean? Let's kind of put it into words. The s is basically the exact sum. Again, that would be a value that we can't find. There is no way to find the exact sum of an alternating series. The s sub k is a partial sum that we are using to approximate the sum with. So that's going to be like our approximate sum. Y'all made it this far in science classes. Well, when you have the exact value minus what the approximate is, what is that basically representing? That's the error. So we have the error is less than or equal to a sub k plus 1. So how I think about that one, s sub k is like all the terms added up to the kth term. K plus 1, the way I think about this is a term that comes immediately after what you added up. So the way I think about this is the first omitted term is often how it's described. And you do want to know that statement because oftentimes you're asked to kind of like prove something about that statement. Again, how can we use that? Say we want to find the sum of an alternating series, and we want our sum to be at least within 0.1 of the exact value. There's no way to find the exact one, but we want to be 0.1 away from it. Well, once I find a term that's less than 0.1, I can add up every term before it, and I know that that sum is close enough to the actual sum. Two ways that question is worded. So here's one way they like to word that question, and we'll kind of talk about the wording as well, a little bit larger. So we'll have, hey, we have this series. Looking at this series, we're going from 1 to infinity. I can see it's automatically alternating, so I can use this error bound. And it's over n squared. And it is converging to a sum of s. Again, we don't know what that sum is, but it is converging. And it's telling us that it's converging, so we don't have to prove that it's converging by the alternating series test. And it says the partial sum p is given by, and they're often going to write it out so you can kind of clearly see what you're adding together. So they've added together the first term they've added together the second term and the third term. So this is a sub 1, that's a sub 2, and that's a sub 3. And then they found that partial sum. The idea behind it is we're thinking that this series approximately adds up to 31 over 36. We want to know how far off that 31 over 36 is from the actual sum, basically. And so it would just be worded like, hey, show that s minus that partial sum is less than 0.1. So what thing you want to be able to do is kind of recognize this as that formula. So again, you're asking like, hey, this is the error. Is that error less than 0.1? Visually, what that means, if I want to kind of think about it on a number line, we have this partial sum is 31 over 36. We want to show that the actual sum is within 0.1 on either side of that value. So like that's what the error means. So we want to show that the actual value is somewhere in that interval. Is that going to be close enough for an approximation? So how we do this is we're literally just going to kind of use the theorem in our justification. So when I'm looking at this, this is from the theorem. So I have that is the error. That's what I have. From the theorem, I know the error is going to be less than or equal to which term?
A sub k.
A sub k plus 1, the first omitted term. So I want to identify what the first omitted term is. Well, to get this sum, I added up a sub 1, a sub 2, a sub 3. So I know that this error is going to be less than which term? Which is the first term that we didn't include in that sum? A sub 4. So that's what I'm going to show. That's basically what the theorem states. So let's go ahead and find it. Well, what is that fourth term? They gave us the formula. Plugging in 4 for n's, that's going to be -1. 4 minus 1, so that's going to be a negative number. But again, we are doing it in the absolute value of it. So that's going to be -1 over 4 squared, which is 16. Well, what is the absolute value of -1 over 16? I'm just going to put it in a decimal just for comparison. 1 divided by 16 is 0.0625. Well, is that decimal less than 0.1? Yes, and we have shown that. So I'm just going to write the statement showing that. A lot of students make this more complicated than it is. Like they think there's something to like calculate, but it's just saying show. Remember on the AP exam when they say show, they're giving you the answer. So we have shown this is basically from the theorem. And then this part is basically from the question. How are we interpreting that? If you could add up an infinite term, only using those first 3 terms will have you within plus or minus 0.0625 of the actual sum, which is pretty close if you think about the whole scheme of things. If you wanted a more accurate approximation, you would just keep adding decimals to that. Yes, Dan?
What happens to like the a sub k minus 1? Is that
It's a sub k, which I didn't write down wrong, plus 1.
So wouldn't that be a sub?
So like the sum is coming from, like if you're adding the first 3 terms, that's like s sub 3. So the approximation is going to be less than or equal to the term that immediately comes out, which we didn't include in that,
So what would, that would be a sub 3 plus 4.
which is 4, which is what we found.
Oh, a sub 4. Oh, k plus, that's in like a sub k plus.
Oh no, this is all like in the subscript. Here's another way where they ask it, and I'm just going to kind of show you the full question and then see how you can approach it. Later in this unit, this is basically going to be after the quiz, this is where we're going to kind of wrap up today. We will see that the following is true. So like, just trust me on this for now, but like, this is a short version of a Taylor series, and that series is the equivalent of 1 over e. That is what it converges to. So you're just going to trust me that that's true for right now. And it says, use that fact and that table of values given to find an estimate of 1 over e that is within 0.001 of the true value of 1 over e. Now I know we have calculators, and you can just like type in 1 over e and figure out which one works. But let's use the idea of the theorem to help us out. We're basically trying to show that the error is less than or equal to 0.0001. So we need to figure out which s sub k, which partial sum do I need to go and add up to where that partial sum is going to be within 0.001 of the actual value of that series. So looking at that table, how many terms would you need to add up
7.
to get within 0.001?
7.
And again, you want to think this is the first omitted term. So if we want to be exact enough, what's the least number of terms I'm going to have to add together?
First one should be 6.
So I'm looking, what's the
6 or 7?
first term that's going to be less than 0.001?
Oh, 3.
So if I'm looking at it
7.
like 6, that's bigger than 0.001, because it's 0.0013. So that one's bigger than it. What about this last one in absolute value? This is the first one that's less than 0.001. So what does that mean? That means that if I added up terms 2 through 6, that sum is going to be within 0.001 of the actual value of 1 over e. And that's like another way how that theorem is going to be asked if I wanted to write like some like notation for that. What we're basically saying is that 1 over e is approximately, adding those terms together, 1/2 minus 1/6 plus 1 over 24 minus 1 over 120 plus 1 over 720. How close are we? That value is within 1 over 50/40 of the actual value. Which is pretty darn accurate for only having to add up 5 terms of that series. We'll see a lot more of this kind of in the second half of the unit when we are actually using these things called series to approximate like long constants. Like we can write series for like e, not like pi, 'cause it's not really a repeating one, but like natural logs and e and even trig functions. We can approximate with different series. So like when we talk about these, we'll be like, well, how accurate an approximation do we need? Look for like the first term that works and just drop 1 term below that. And adding up those terms together would mean that sum is within the approximation that we're looking for. Questions on that? Kind of getting deep in like the theoretical aspect of this. All right, so that is where I'm going to go ahead and stop today's notes at.